So I marked down the couple that I knew who you were. All right, I'm gonna go past this. This was meant to be a video time, but I don't think many of you guys had time on it. So, quick reminder: compositional stoichiometry. Okay, you were. Let's go to this again. You were pulling your notes from yesterday. Boys, pull out your notes from yesterday. Pull out your example sheet that I gave you yesterday with your lecture notes on it. And if you don't have a calculator, go ahead and grab a calculator. Let's get this going. Let's roll. Yeah, you got to reach the left and you have empty boxes. Always okay. All right, we're going to get started in like 20 seconds. So you guys got to know how to get ready for class. So pull up your stuff for me, okay? Who has their mole map right in front of them? Mole map right in front of them. It's a little map that you made bubbles with yesterday. It's feed in time symbols so you can looking forward. And you guys can see the time symbols so you can see a little bit better. Okay? That's if you're in an awkward place. Alright, so you have this pulled out for me. Ta-da! What was the relationship between mole and particle? This table up here. Let's go. Mole and particle. Good. 6.2 times 10 to the 23rd is Avogadro's number, right? Mole and molar mass. Back table. Corbin's table. How is that related?
It depends on the element.
Okay, so it depends on the mass from the periodic table. So we look for the element or the compound and we add up their masses. And then lastly, how is the moles and the molar volume related? Elizabeth's table. Right, 22.4 liters per 1 mole of gas at STP. So on your reading guide, what did it say for STP? Anushka's table. What's STP stand for? And what were the variables that standard temperature and pressure were? Like the numbers. Mm-hmm.
0 degrees Celsius, temperature 101.3. Let's say kPa or 1.
Right. So 101.3 or 1 atmosphere, those are both the same. They're related. They're one and the same. And then 0 degrees Celsius is what, Kelvin, guys? 273 Kelvin, right? So STP means standard temperature conditions and standard pressure conditions, which is just what they do. Okay, so we're going to add on to our notes today. I gave you one example yesterday, but we're going to fill in some of the blanks that I provided here. And on your sheet, I don't start here with you on your sheet, but let's just recap this so that we have our background really solid, okay? So the whole concept is basically an SI unit. That SI unit is very important, and therefore we are using it a lot. And it's going to allow us to relate a couple of variables which we've just discussed. So the definition of the mole will allow us to convert between what and what? Mole and loud and proud. Particles. And particles come in 3 flavors. What are they? Atoms, formula units, and molecules. Okay, so that's like literally the definition of the mole. But we know there's other relationships from our mole map, right? Mass and volume. It's just not specifically from that definition of the mole. So we know we can count stuff. That's a good thing to note. 2 things I wanted to tell you from these pictures. When we're looking at particles, they come in a variety of ways that we can see them. Well, we think we can see them the way we illustrate them. So this is neon, right? ... We call that monatomic. And then we have hydrogen gas over here. Notice there's 2 dots connected to each other. Remember these like particulate diagrams we did way back? We actually looked at little cards. So this is called diatomic. Can anybody maybe postulate why that's the case? Di means 2. Mono means 1. So neon exists in a singular fashion. Hydrogen gas exists in a little double, and as do a couple of other things. So if I ever say diatomic, it just means 2 atoms connected to each other. So if we're looking here, what's Cr2O72 minus? Nope. Dichromate, right? So this is dichromate, and dichromate is attached to so there's dichromate, it's attached to an NH4 plus, which is ammonium, and another one. Okay, so there's 2 of them. So what's the name of NH4 to Cr2O7? Ammonium dichromate. Good. And so that's reacting or decomposing to make Cr2O3, which is what? Not chromium. That's not an ion, so we can't just call it out as an individual ion. It's going to be a compound. Two names. Cr, chromium, and then O, oxide, right? So then put that together. Not, almost. So it's don't you say tri? That is a prefix for covalent. Chromium oxide is what we want to say, right? But we see chromium, we're like, that's chromium's that what? Transition metal. Somebody else also have to say. Chromium 3 oxide. Okay, so ammonium dichromate decomposes to chromium 3 oxide, diatomic nitrogen gas. Okay, so it's just diatomic, it's together, and then 4 water molecules. So that's just how we would illustrate them, or we would describe them if we saw a reaction. But what you're seeing is that there's 1 as a coefficient, 1, 1, and 1. So we're essentially saying to each other with those coefficients, 1 mole of ammonium dichromate decomposes to form 1 mole of chromium 3 oxide, 1 mole of nitrogen gas, and 4 moles of water. So we can create a ratio or relationship using reactions as well as relationships that we've already described. Okay, so this is where I think you pick up on your paper. Yes? This one with blank right here?
Yeah.
All right. Do not worry so much about writing any of this information down up here. This is just describing what atomic mass is, but we kind of already know what atomic mass is because we've dealt with it before. We've worked with it from the periodic table. So, but what it's trying to indicate to us is that the mass of 1 mole of any compound, so a compound or any element, is called the atomic mass. So 1 mole of any compound is called its atomic mass, or its molar mass. So they used to describe or define, all these chemists used to define the molar mass as this quantity here. The average mass of 1/12 of a mole of carbon. But I think you guys wrote that definition down in reading guide 10. AMU, atomic mass, someplace in there. I can look. So I was going to say just start on your chapter 10 reading guide. I thought it was question 4. Okay, well, regardless, atomic mass or molar mass is how we define the mass of any given compound or element. So let's fill these in together. The mass of 1 mole of sulfur is, drum roll, you're looking at a periodic table and you see what? Yeah. All right, everybody sees what on sulfur? 0.7, right? All right, so we've been calling that AMU, which is atomic mass units. But atomic mass units are representing mass, which we like to actually use what unit for mass? Grams, because we literally can mass things in grams, and so that's our preferred unit. So there is a relationship. So we're going to call out everything from here on out from the periodic table as grams. Okay, so the mass of 1 mole of sulfur is 32.07 grams. How many atoms? Okay, so when you see atom, which of the 3 branches are we talking about? The first one, which is like overall, that's called what? Particles. Okay, so how many particles are in 55.8 grams of iron? What's the significance of this number, Aiden's table? That's the mass of what?
Iron.
So 1 mole of iron. So the periodic table is saying that's the mass of 1 mole of iron. So then if that's the mass of 1 mole of iron, everybody, how many particles should be in that 1 mole? Yeah, so Avogadro's number. So 6.02 times 10 to the 23rd particles. So you're relating mass in atoms by the relationship that they both have to mole. And then lastly, if I wanted to have 6.02 times 10 to the 23 atoms of carbon, what mass would that relate to? Why 12.01 carbon? Which we're saying now the mass on the periodic table is the mass of a mole of carbon, right? So 1 mole of carbon weighs 12.01 grams, which is related to that many atoms. So you see all these relationships pieced together. So we're going to practice just maybe on 2 of these for clarity to make sure that we are okay with calculating molar mass. Sometimes they get complicated because of the subscripts involved, but most of them they're pretty straightforward. So let's start with let's start with water. Okay, let's keep it simple. I have how many atoms involved total? 3, right? 2 H's and 1 O. So 2 H's. Put 2 to represent those 2 H's, and then we're going to multiply this by the mass of hydrogen, which is what, Cole's table? The mass of hydrogen. 1.01 grams, right? And so we're saying 2 hydrogens, and we're going to add that to the last atom, which is 1 oxygen. And so, what's the table? What's oxygen's mass? Straight 16, okay? So 1 times 16, or just, add 16. So we can maybe approximate this. What's 1 times 2? 2, and then 16. So total that up and you get what? 18.02. Good. All right, so we can't just write 18.02 because this is molar mass. So I must have both of those units on my number to describe the measurement. So we call that out as 18.02 grams per mole. 18.02 grams per mole. Okay, so that was a simple one. Let's attempt what's the name of this? Magnesium nitrate, right? Okay, so consider in your group how many atoms you have of each element. Add them up. Go. Add up their mass. All right, so help me out, SDs. How many magnesiums do we have? 1 magnesium. What's the mass of magnesium? Okay. Anushka, how many nitrogens do I have? 2. So here's the deal. This 2 subscript applies to everything as a multiple on the inside of the parentheses. So N technically has a 1 after it. So 1 times 2 is 2. So there's 2 nitrogens, which is 2 times 14.00, right? Or is it 14.01? 14. Your periodic table might say 14.01. Different ones sometimes claim different ones. Okay. And then how many oxygens does this claim we have? 6. So 6 times oxygen is 6 times 16.00 grams. And then what do we get when we add that together? 148.33. And that would be grams per mole. All right, give me a thumbs up if you get how to calculate molar mass, and you could do it from anything. Parentheses matter, right? So just make sure you're applying that subscript. All right, and so you'll notice there's more examples that if you wish you can do, and I can help you with those as well. Okay, that's not what we need. Okay, so the last piece is just to verify what you need to know definitional-wise of molar volume. We literally wrote down pieces of this yesterday within our mole map. So I just want to clarify, we were talking about molar volume of a gas, because gases spread out a whole lot. They take up a lot more space than we think they do. So like a mole of water in its liquid form is going to take up like this much space. That's about it. Less than that probably. But a mole of a gas, because gas particles, so water particles are really, really close together. Gas particles are very, 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 very spread out. So a mole of gas would take up, that's not even 22.4 liters, but it'd be more than that. And that's just because the 6.022 times 10 to the 23rd particles would be very, very spread out. So therefore, they would take up a lot of volume. So it's a confusing way to think about it sometimes, but 22.4 liters is really not representing very much. It's not representing more particles than this little bit here is of water. So 22.4 liters is representing moles of gas at standard temperature and pressure. Okay, and you have this down already, yes? Moving on, okay. So we went through this one yesterday. Let's pick up here. This is the second example on your sheet, yes?
Yes.
All right, so everybody needs to write down the thought process if you need it, but specifically you need to write down the mathematical application, which is dimensional analysis, and we're canceling units. It's old news. It's just applied in a new setting. All right, so we're starting off with what given, guys? Everybody. 32 moles of who? Potassium. That's K, right? So check, we've written our given down. We're going to who? Grams. And I want you to write down your little bracket thing. And I want you to touch on your mole map. Where's your mole map? Right on the back. Touch on your mole map with 2 units that we're comparing between. Kern, where are you touching? Between what and what? Okay. I'm gonna grams and moles, right? So can you guys? This blue is kind of fading, but I think you guys can probably see what I'm using here. All right. So we know that between moles and grams, the relationship is what? PTOE molar mass, right? So we're gonna have to look where for the mass of potassium, right? So I have to go to the PTOE, and what's the mass of potassium? 10, what per what? Grams per mole. And so we are assuming when I write per mole, how many moles am I speaking of? 1 mole, right? We already knew that because we always have a big O 1 next to the mole when we make this relationship happen. So where do I put mole on my bracket here? Bottom. So 1 mole of potassium is equal to what? Thank you. I don't know who said that. 39.10 grams of potassium. What unit cancels? Moles and moles. Do not cancel the numbers out. The numbers are utilized for calculation purposes and calculate. So 0.32 times 39.1. Go for it, Corbin. And any more numbers?
There's 2.
2. And that's grams of potassium. Good. So all we did was 0.32 times 39.1. How many sig figs should be here, guys? 2, because our initial measurement was 2 sig figs. So how would I round this? Good. I want the 1 and I want the 2, but I look next door to 2 and I see a 5. What happens? It rounds. So 13 grams of potassium. And that's your answer. Okay, so let's go a little bit more complex. Because the first 2 examples we did, we went from particles to moles using what conversion? Avogadro's number. We went from moles and grams using molar mass. So let's scooch down to, actually let me do 4 before I do 3. Okay, start off 4 for me. Start off the setup. You need to have a calculator if you don't have one. If you can't adequately show your work on the computer, I can get you some paper, like on your lecture sheet. So don't try to squeeze it in there. You need something to study from. So I would assume that you are able to do this. You don't need me. As long as you know what sodium phosphate is, you should be able to get what you need to get. right, what'd you get for your molar mass of sodium phosphate? Shout it out for me. Starts with a 1, 6, 160 what? 1. Oh, for sulfur. Sorry, I had to do that comes from memory. 30 point. This phosphorus is molar mass. 30.97. So 163.94-ish. Okay, like I said, some periodic tables will have a slightly different decimal. I've got one partially memorized in my head, so if I use something slightly different from you, don't take offense. It's just going to be super close. Our answers will be super close, so we're good to go. Okay, so basically our thought process was we saw moles, we want to go to grams. There's only one relationship that we must consider. Moles and grams have a relationship of using the what? Periodic table. I would love some more participation. Okay, so I need to know that you know your what you're thinking out loud here, okay? So that relationship is using the periodic table. Therefore, to cancel moles out, we have to put on the bottom. 1 always goes with mole, unless it's, of course, given to us initially with a non-1. That 1 mole is related to the molar mass of sodium phosphate, which adds up to 163.94. And what do you guys get when we, what units are going to remain with us when we calculate? Grams, right, because moles will cancel. So we'll have grams of sodium phosphate. Okay, and then what's this equivalent to? Estes? What's our answer? What's our answer? Mathematically. 0.741 what? Sorry, did you say 008?
Yeah.
Okay. And so, how many sig figs should we have?
5.
Not 5. We're getting 5 from. So you're going to go with the measurement. So the molar mass is important, but like that's going to have a lot of sig figs. So we're pulling a lot of decimals off the periodic table. But this is our measurement. How many sig figs are here? 3. And so therefore this would be rounded, like you said, to what? Is this right? Okay, I like to get a double check on everything. I did not calculate with you guys. Okay, so 0.741 grams for sodium phosphate. All right, now let's do, I'm going to show you, no, go ahead and do 6. You can do 6 on your own. I need to show you 3 and 5 separately because they take it one step farther. I think it's beneficial for you to touch on your graph, mole map, the steps you're going to take. Notice I said steps. Think of the steps. Bailey's table, tell me your first, your first step, which would be like your first thought. Okay, why am I converting formula units to moles and not straight to grams? Right, you can't do that. So everybody has, like, I think if you know this, you're going to be fine if you track yourself along this path. Particles is a formula unit. There's only one connection. It's got to go to mole, right? Bailey, once we get to mole, where would we go next? To grams using what? Hero table. So this is a 1-2 step process. So that's why I said steps out loud there. So tell me how you're doing this one, this first step.
Right there.
And why are you putting this down here? Okay, so this represents the number of formula units, right? So this represents the number of particles, therefore we want formula units on bottom. So to cancel those out, that's why I have to put that there. So this is formula units of lead 2 iodide. And that's related to 1 mole of lead 2 iodide. Because the 1 always goes with the mole, and the formula units must cancel. Done, done. Okay? We're not going to calculate yet because we're not done. Aiden's table, can you guys tell me what your next step would be? Because now I've canceled out formula units, and now I need to cancel out mole. So get me started. Mm-hmm. So give me some numbers. Tell me what I'm writing here on top and bottom. So somebody at your table add, somebody else tell me here what to put down units wise maybe. So 1 mole at the bottom, 1 mole of lead 2 iodide at the bottom, because that's going to cancel. And then you're putting grams of lead 2 iodide at the top. Okay? Everybody, what's that molar mass? 461, pretty much on the dot, right? Okay, so then did you get that, Elizabeth? Okay, so lead and 2 iodides together, and then mole cancels, and the only unit left is grams. Yay, that's what we wanted. And then as you guys calculate, what do you have to put? Parentheses, or we're going to get wrong answers. So does anybody have an answer? Raise your hand. Okay, just gonna let everybody else catch up with you real fast. I got one person that has the answer. 2, 3, 4, keep your hand up. Can I get more than 3 of us? Maybe you can check with your partner next to you before you shout it out loud. All right, and start me off. I'm good with that. Okay, stop. And that's grams of lead 2 iodide. And then everybody, how many sig figs should I have? 3 from here. And so we'd round that to what? Grams of lead 2 iodide. Yay! Okay, so that was a true thought process because you had to go from particles to moles, moles to grams. Now, back up to 3. Notice what's weird about this question. It starts us off with what? Moles of what? No, it's not an ion, so you can't call it that. It's not an ion, so it can't be one thing. It's a compound. Sulfur trioxide, thank you. So it's SO3, so it's not charged, it's not an ion, so you can't call it sulfate, sulfite, sulfur, whatever. Okay, so you just got to call it out as first name, last name. So we're going from moles of sulfur trioxide to what? Atoms of what? So we're going from apples to oranges, so it's weird, right? All these other ones have been go to same thing, the same compound. So we're going to have to dissect this one a little bit more, okay? So essentially, I can look at sulfur trioxide, which is a molecule, right? I could even draw it out. Looks like this, kind of like this with some electrons around it in the right places, like we'd have to count out valence electrons and everything. So I can look at this and actually make my own ratio. I can make my own conversion factor, which is going off-road here. Okay, so it's not on our map. So if I look at this, I say in 1 molecule of SO3, I have how many atoms of oxygen? 3. It's obvious, right? You can look at it from a subscript perspective, you can look at it from a drawing perspective, but we've made our own relationship, and it's a very valid one. 1 molecule contains 3 atoms of O. So that is our last piece. That's how we're going to get from molecules of SO3 to atoms of oxygen. So save this piece for last. Can you get me started? Yes, you can get me started. Go. Get started and then use this piece last. I've given you a hint on where to go to, at least. Alright, so I think some of you guys are picking up what I'm putting down. Bryce, what is our obvious first step? Okay, and we only have 3 options, right guys? Mole is related to 1, 2, 3 things, right? Who cares about grams here? No one, right? There's nothing related to grams at all. Who cares about volume of here? Nobody, right? Nothing regarding volume. So what's the only one we really care about? Particles. We're trying to get from moles of sulfur trioxide to its particle form, which in this case is what? Sorry, what is the particle form of a covalent compound? Molecule, right? So I put particle there as like the big word, big umbrella term. But yeah, we're going to a molecular form here. So yes, you said use Avogadro's number. So 1 mole of sulfur trioxide contains 6.02 times 10 to the 23rd molecules of SO3. Okay, so now we've gone from like the unit of mole to the unit of molecule. Notice I wrote MOL and then molecules, so you know they're different. Don't just put MOL for everything, please. Now we're in this molecule, and this is what we're looking at right now. Now get me smaller. Go deep into the molecule. 3 atoms of O is equal to 1 molecule of SO3. Because I have to cancel molecules, so I'm going down to the place where I'm sticking with molecules, so I need to cancel that out. So mole and mole cancel, molecule and molecule cancel, and I'm stuck with atoms. Yay, that's what I wanted. So calculate. Help me out here. What is it? 24th atoms of O. You guys gotta be louder. Your colleagues cannot hear you at all. Okay. And 3 sig figs all the way. Okay, so I would make an adjustment on your mole map because this is generically what we get to use all the time. I would say particles can go out kind of off-roading to a singular atom. So you can do ratios. So you can make your own ratios between like molecules and atoms, just if you need to. Can I scroll down from here? Yes or no? Yes? Okay. So I want you to attempt number 5. Number 5. Number 5. Attempt number 5. The last one we do together. thumbs up if you think you're on the right track. Okay, grab my calculus. On your mole map, some of you are calculating, you're fine. But if you are not okay, go ahead and touch your mole map where we're starting. Just on your own. Where are we starting on the mole map? Everybody should be touching what? The volume, okay? There's only one thing we can do with volume. What is it, guys? Convert it back to moles using what relationship? 22. Thank you, 22.4. I have to use that first, right? So if I'm starting off with liters, liters must go on bottom to cancel. What number has to go with liter? 22.4, and that's liters of CO2, but that's related to how many moles? 1 mole. Give me a thumbs up if you could get the first step easy peasy. Give me a thumbs up. This is my way of assessing you, so I don't have to just quiz you all the time, okay? So help me out here, okay? So yeah, liter to mole is an easy first step. Now, there's a couple ways you could attempt this problem, but I'm going to stick with the one I think you guys would have probably gone to. You probably would have gone to what next? Moles to particles, right? Because you're trying to get down to this like particulate level. You're trying to get down to the atomic level. So you guys are probably, I'm thinking going to molecules next. So who did go to molecules next? Okay, so in 1 mole of CO2, 1 big mole, how many particles are there? Okay, and that would be what style of particle? Remember, particles come in 3 flavors. Molecules. So we're going to molecule because it's a covalent compound. Okay, so everybody do this for me now. Pick 1 molecule of CO2 out of the air. Okay, you grabbed it. Everybody pick 1 molecule of CO2 out of the air. You grabbed it. You're looking at it. Okay, what's inside of CO2? 1 C and 2 O's, right? Well, we're actually saying 1 atom of carbon and 2 atoms of oxygen. Can you guys stop talking for a minute? Thank you. All right, so 1 molecule of CO2 contains 1 carbon atom and 2 oxygen atoms. So what am I trying to get you to see? Trying to get you to see what? There's 2 oxygen. There's 2 oxygen atoms in 1 molecule of CO2. Try to get those terms out there. So our last step would be molecules have to cancel, right? So 1 molecule of CO2 contains 2 atoms of O. Think of it like a Reese's cup, okay? So when you go to the store and you get a package of Reese's cups, you get the whole package, right? What's inside? 2 Reese's cups, but you got 1 package, but what's inside? 2 candies, right? So this is the same thing. You grab 1 molecule, but inside there are 2 of the things you're interested in, 2 atoms. Reese's cup example, okay? So as you calculate, anybody? 1.34 25th atoms of O. And that makes good sense except for the sig figs, so 1.3. Okay. All right, so give me a scale of 1 to 10. How do you feel about the 6 examples we've done here? Scale of 1 to 10. I need some hands up, people. All right, so on those of us who are not at like 8s and 9s, is it the ratio thing? Is it that one that's kind of throwing you off? How do you feel about like all these connections? 1, 2, 3. I'm working on reading your mind. It's not working. Thumbs up, thumbs down, something. Okay. All right. To me, it looks like you guys are doing okay. Okay. So let's do a quick activity, and then we'll jump into the 1 through 8, which is what I'm asking for. Complete, finish 1 through 8, and we'll do some of that in class together as well. So what I need everyone to do is listen first. Okay. As I say this, you'll know what we're doing. Maybe. Look at a partner. Name them with your eyes. Wink at them. I don't know. Okay. In a moment, you're going to go to the lab station and you're going to grab a piece of chalk from right behind her. You can have one collectively together as your partnerships. You're going to initially mass your chalk. And then you're going to meet me at the door. So you're going to do what? Grab your chalk, mass it, Near the door. Go.
Who doesn't have a partner?
Somebody needs to map, somebody needs to get the scale up and going. You need to zero out your scale first, of course. Zero out your scale first. Guys, let it zero, let it count down, let it get stable first. Go write your number down on your notes real fast. Write your number down on your notes real fast and meet me at the door. And bring a jacket. It's cold. You don't need a jacket?
Don't have one.
Yes, with your piece of chalk, meet me at the door. All right, we need 10, 9. Write down the number out someplace because you're going to forget it. 7, 6, 5. Meet me at the door. 3, 2. Meet me at the door. 1. Okay, so listen. You can only write cool chemistry things. Spell your name on the periodic table. I heart chemistry. Miss Edie's a good teacher. Good positive things. Okay. So go out and to the left and go find a sidewalk to right on. You only have a couple minutes because it's code. Okay. Go. Be quiet in the hallway. Grab your comments. All right, so this is what you were doing. When you come back in, go back to the lab. I'm sorry, grab something to write with. Grab something like if you're writing this in your notes, that's totally fine. Grab something to write with. If you're writing this in your notes, that's totally fine. You're going to do a quick math with me, okay? Grab something to write with. If you're writing in your notes, that's fine. Go back to where you were going to math, and let me tell you what I'm requiring of you. No, this could be within your notes, that's fine. Okay, so stay at the last station and listen up. This is all I need. Wait before you were writing on the chalk, on the sidewalk. That's a mass you already have, yes? Yes? Okay. Wait after, figure out how many grams of chalk you actually used, convert that to moles, and convert that to formula units. You have about 6 minutes. I need to tell you what chalk is. It is calcium carbonate. Go. Okay, and jump in bigger. Okay. And jump in bigger. Thanks, darling. This will be written down in everybody's notes or in everybody's paper on their form. It's not a individual. Bailey, do you realize we
There's another charge.
Mind the way?
So we started with 1 mole. Now there's moles.
Oh, you guys have about 2 more minutes.
What does that mean, grams? About how much do you guys like, we just take one?
Yes, carbonate.
This was asking
Okay, so what's the right here?
I was definitely like, that is not calcium carbonate.
All right, I'll see you back at your desk. I do need you to do two things for me. One, it's okay if you're not done, you can finish at your desk. Two, chalk these come back into the little bin. Three, these scales need to be put back the way they were found. Chalk back, scales back. Let's go. I'll see you back at your desk in 10, 9, let's go.
You can talk at the time.
Eight. 6, let's move it. 4, please come back to desk. 3. Scales should be back, chalk should be back. 2. Veneer, Chandler, Camilla, thank you. 1. Okay, so let's recap. This was not a very challenging exercise. I think a lot of us got caught up on what calcium carbonate is, but we finally got there. I tried to correct you. Everybody had a different gram of chalk used. So we had 12 and 5 and 9 and 14. Everybody had a different number of grams of chalk used, right? So how did you guys get from grams of calcium carbonate to moles of calcium carbonate? How did you get there? Using what? Here, our table molar mass, and everybody should have the same exact molar mass. What is the molar mass of calcium carbonate? 100.09 grams of calcium carbonate. So this number is different for everybody, but the conversion is exactly the same. So everybody got a very little, small amount of moles of calcium carbonate. So that's going to get you to this step here. And then I added on here formula units because I wanted you to do more practice around with that. How would one get from this information to formula units? Use Avogadro's number. So whatever you got for moles, you would just use Avogadro's number to convert to formula units. If you've not finished that up, finish that up, show your work, and then I'm just going to come around and check that you did it because that's going to be like an activity, right? And then as I mentioned before, you were working on 1 through 8. I'm going to give you guys the rest of class, and I'll turn on announcements if they're even up. But that gives you about 18 minutes to work on 1 through 8. I'll be right there. So I need to be able to see where they are. So make sure they're labeled, something. Yeah, keep it organized. So on the U practice 1 through 8, I'll put the answers up here at the end of class so you can at least check yourself out and reference how far you've already got. But that's, yeah, this one's. So you see particles, so the particles specifically ask you guys to convert to like molecules. So what if this is calcium carbonate, right? So you just feel it from see? Ionics is the right word and particles really change. I print out these lectures for you so you have a nice reference and you don't have to write the questions down and all that stuff. You need to show your work very clearly. So if I took it from you, I would want to take every single note you've ever taken, right? So if you put it on the lecture notes, one, it's too tiny for me to even check, and two, it's not very easy on my eyes for study purposes. Can I have on a subject paper if you don't mind? We learned that so much at the game.